All right, so now let's talk about our first category of reactions. These are double displacement reactions. Double displacement reactions occur between ionic compounds. Usually they're in solution, so usually these would have these AQ designations. And you'll notice that these ionic compounds are swapping their cations or swapping the anions, whatever way you want to think about it. But my cation over on this compound is going to combine with my anion on this compound to make my new compound over here. And similarly over here, this cation is swapping with this anion to make my new ionic compound over here. Right? So these are called double displacement reactions. There's two like subcategories of these that we're going to talk about: precipitation reactions as well as acid-base reactions. So first, let's talk about precipitation reactions. So let's actually just zoom in on our little picture here. This is when we mix two aqueous compounds together and a solid is formed. Okay, so over here I have sodium iodide, and I'm mixing that with lead nitrate. So, so this beaker here contains sodium iodide. This beaker here contains my lead nitrate, and I'm going to mix those together. And what happens is the sodiums and the nitrates don't really do anything, but the leads, so here was my lead. Use a different color. This is my lead ion. Will find my iodide ion, and they'll start forming a solid. So they'll start precipitating out, meaning forming a larger solid. And so that's what we see here going on. It turns out that this lead iodide is this really pretty yellow color. So as soon as you mix these, you'll see this bright yellow color form, and it's a solid. So it will end up settling all the way to the bottom of your beaker. Okay. So if we looked at the balanced chemical equation for this, we have two aqueous compounds, two aqueous solutions that we're mixing, and we're forming a solid compound as our product. All right. The other two ions remain aqueous. Okay. So this is a precipitation reaction. This lead iodide is precipitating out. We actually already know how to predict whether or not these precipitation reactions will occur because of this chart here, which we gained some experience using before, right? We have this, so it was sodium iodide plus lead nitrate mixing together to form sodium nitrate and lead iodide, right? And using this table, we can prove to ourselves that indeed this compound here is soluble. This compound here is soluble, right? Because nitrates are always soluble, just like sodium's always soluble. There are no insoluble exceptions. And so sodium nitrate is definitely soluble. But lead iodide, we would have found using this table here that iodines are usually soluble with the exception of being paired with lead. So we know that this is an insoluble compound, which is why it's a solid that's formed. Okay, so this is going to be all about predicting whether or not these precipitation reactions actually occur, and you're going to have to use these charts here. You're looking for the formation of a solid product or an insoluble product. Okay, so again, let's just sort of first make sure that we can use this table. Silver nitrate, calcium sulfate, and potassium carbonate. Because again, the first thing we're going to have to do is be able to recognize whether the products of these reactions are insoluble, right? So this is the same thing we did using this table previously. We just want to be able to make sure that we know how to use it. So sodium nitrate, silver nitrate, I'm going to go to my table here, get rid of all this business. And I see that for nitrates, there are no insoluble exceptions. So this is definitely going to be soluble. Calcium sulfate, I'm going to go to my table. I need to find either calcium or sulfate. In this case, after I hunt around a bit, I will see that sulfate is located here. It says most sulfate compounds are soluble, but calcium is an exception. So this, whoops, this compound here would be insoluble. And lastly, I have potassium carbonate. If I look at this table here, I see potassium and there are no insoluble exceptions. I can also double check because I got carbonate down here and potassium is a soluble exception. So in this case, this compound is also soluble. All right, so why does this matter? Why do we need to do this? Because you're going to be given something like calcium nitrate plus sodium sulfate. And you're going to be asked, is there a chemical reaction that occurs? And so what you're going to do is, following the format of the double displacement reactions, you're going to take the cation and the anion and swap them. So this would make sodium nitrate. And then you're going to go to the other one, do the same thing, take the cation and the anion and swap them, plus calcium sulfate. And you're going to know that your starting reactant, your starting materials are both aqueous, but you're going to have to figure out what the state of matter is for the other ones, right? And we know that you can look on the chart that nitrates are always soluble, so this will remain aqueous. But what that chart told us is that calcium sulfate is insoluble, which means that this would be a solid that's formed. And so this would indeed be a precipitation reaction. Okay, so given your reactants, you swap, write your products, and then look them up on that solubility table to see if any of them are insoluble. So then the last step here would be I would have to balance this. I'm just going to do it quick, but yes, there would be a 2 out front there, so you guys can convince yourself that that makes it so that my equation is balanced. All right, but again, just to finish my color coding here. All right. So anyway, these are these double displacement reactions, and this is just using the same example where it shows that lead iodide is a solid, and I knew that because I could find it as an insoluble compound on that table. Okay, so now talking about ionic equations and net ionic equations. What we're going to do, so just to give you sort of the background here before I start going into the details, an ionic equation tells you what's happening to the individual ions, right? Because if I put, for example, sodium sulfate in water, it actually breaks up into its 2 individual ions, right? There's sodium floating around all by itself and sulfate floating around all by itself. One of those may not participate in the actual chemical reaction. So that's what we're seeing when we write our net ionic equation, is kind of like the meat of what's going on. Are there ions just floating around and not doing anything? Or is there an actual reaction? Okay. Here's an example of going from a complete ionic equation to a net ionic equation. I think it'd be just better for me to start from scratch here. So what we're going to do is we're going to write our balanced chemical equations first by predicting that there was this trade of anions or trade of cations, right? Doing the swap. And then we're going to separate the aqueous compounds into their constituent ions. All right, so what do I mean by that? Let's just do one from scratch here. Let's do, so what happens when I mix silver nitrate and sodium chloride? All right, it's a good idea to pause the video and try to write the products of this reaction and look them up to see if any of them are going to be insoluble. Okay, I'm going to go through it, but it'd be a great idea for you to practice it on your own. So I'm going to swap my anion and cation. So silver chloride, that would be this new compound over here. Same thing over here, anion, cation, sodium nitrate. And again, I knew that these were aqueous to start out with, but now I'm going to have to figure out what the state is for my products. So I'm going to look up silver chloride on my table. Get rid of this. Okay, and I found my chloride ion. Most chloride compounds are soluble with the exception of silver. So silver chloride would indeed be a solid that's formed. Sodium nitrate, I can look this up on the table. Nitrate doesn't have any insoluble exceptions. Same with sodium, actually. So this will be a soluble compound, otherwise known as aqueous, right? So step one was I had to use the table to figure out what my subscripts are going to be. Step two is I'm going to break up all my aqueous compounds into their constituent ions. So what do I mean by that? Silver nitrate is composed of silver, a silver ion, and a nitrate ion. So when I'm writing, this will be my complete ionic equation. I'm going to take everything that's aqueous and break it up into its different components. So this and this, same with sodium, becomes the sodium ion and the chloride ion. Okay, need to manage my space here. Okay. If it doesn't have that AQ designation, then you don't break it up. All right. So because silver chloride is a solid, I'm just going to leave it as silver chloride solid. It's only the electrolytes or the aqueous compounds that you break up. Now I'm going to, since sodium nitrate was aqueous, I'm going to break that up. Cool. So this is my complete ionic equation. I got my complete ionic equation. Let me use a different color. Complete ionic equation by separating the strong electrolytes into their constituent ions. And again, another word for strong electrolyte is an aqueous compound. Now, in order to get the net ionic, I'm going to go through and cancel things that are on both sides of my equation. Okay, so on this side, I have a silver ion. I have silver over here, but it's not a silver ion. It's not Ag plus 1 AQ. It's not the exact same thing. So that I don't get to cancel. But I do get to cancel this nitrate because it's NO3 minus 1 AQ over here, and it's NO3 minus 1 AQ over here. Likewise, I get to cancel my sodium because it's Na plus over here and Na plus over there, right? Same thing on both sides. And I don't get to cancel my chloride. So my net ionic is what you get at the end, which is so silver AQ plus chloride AQ gives you silver chloride solid. And, you know, notice how, again, it's just kind of telling you the meat of the chemical equation. The sodium didn't do anything. It was just kind of floating around the whole time. The nitrate didn't do anything. It was just floating around the whole time. What happened was a silver ion found a chloride ion, and they precipitated out of solution. So that's what your net ionic equation is really showing you, is the meat of what's happening. Who's really reacting with who, ignoring all the spectator ions. All right, but that's how you would get your complete ionic equation. You break apart all your electrolytes, all of your aqueous compounds into their constituent ions. And your net ionic is when you go through and cancel everything that's on both sides. Okay. All right, so let's do another one. Like the reaction that occurs when the aqueous solution of lead acetate, so it gives me my formula here, PbC2H3O2 plus calcium chloride are combined, okay? And so the premise of the problem told me that these two are aqueous. How am I going to get what my products are? What am I going to do? Swap. Right, so now I'm going to put the lead with the chloride. And I'm going to put the calcium with the acetate. So yeah, so this is how I got this compound. Then I swapped this for this. This is how I got this compound. So what's the next step? Now I have to go through and figure out what is the state of matter for each of my products. All right, so using my chart here, this chart is obviously going to be a very important part of this lecture. So first of all, we have the acetate ion here. It says acetate, there's my ion. There are no insoluble exceptions. So I know that calcium acetate is going to be aqueous. For lead chloride, again, going back to my table, I find my chloride. Most chlorides are soluble, but there is an insoluble exception, which is lead. So that means that lead chloride is insoluble. So this would be a solid. Okay. I got to make sure that everything's balanced. It actually looks like it is already. I have one lead on both sides. So one Pb, one Pb. I'm not going to break up the acetates too. C2H3O2 minus. I got 2 over here too. I have 1 calcium, and 2 chlorines, 2 chlorines. So actually everything's already balanced. That's fortunate. So that's done now. So this is my, what we would call the molecular equation. Now I need, so this is molecular. Now I need the complete ionic. This is where I'm going to break apart all of my aqueous compounds. So lead will become a lead-2 ion. And my acetate will become acetate ions. I actually, so C2H3O2 minus 1, I have to put a 2 out front here because there were 2 in my compound there. So I have to indicate that with the coefficient 2. I'm not going to leave it back here. I'm not going to leave it like this. I have to put it out front, move it out front, because that's how telling me that I have 2 acetate ions. Calcium's 2 plus aqueous. And similarly, I have 2 chloride ions. Right, and again, this 2 here got moved out front when I did my net ionic equation. All right, I'm gonna run out of room. Oh, bummer. All right. So because this is a solid, I don't break it apart. Only the aqueous get broken apart. Running out of room. And then when I do my net ionic, I'm going to go through and cancel everything that's on both sides. So I get to cancel these 2 acetate ions, and I get to cancel my calcium ion. So again, kind of leaving you with the meat of what's going on here. We have lead 2 plus AQ plus 2Cl minus AQ gives you PbCl2 solid. All right, so that would be my molecular, my complete ionic, and my net equation. Okay. The other type of double displacement problem is involving acids and bases, okay? Acids are compounds, they're ionic compounds that have hydrogen as their cation. We learned how to name acids previously, so this would have been hydrochloric acid. And bases are any compound that accepts a proton, but they're easy to spot. So most of them are easy to spot because they have these hydroxide ions in them, okay? So what happens is acids and bases react to form water, all right? So let's see an example here of what I mean. We have magnesium hydroxide plus HCl. This is again a type of double displacement reaction where I'm going to swap my magnesium and put my magnesium and my chloride together. That would be MgCl2. You want to convince yourself that it's not just MgCl, it's MgCl2 because magnesium is magnesium 2 plus. I see that from the periodic table because it lives in column 2. All right, so we can't forget all that stuff that we learned in previous units. And now this is the new stuff with acids and bases. The hydrogen ion and the hydroxide ion will come together to form water. And water gets a liquid subscript. Magnesium chloride is aqueous. I can look that up on my solubility table. HCl is aqueous. But magnesium hydroxide is insoluble in water. So this is a solid. Okay, so now that I have my subscripts on my products, the last thing I'm going to make sure to do is balance my chemical equation. Magnesiums are balanced already, 1 Mg, 1 Mg, but the chlorides are not. I'm going to have to move this over. I'm going to have to put a 2 out front here so that I have 2 chlorines on either side. Now I can go for the harder part, which is the hydrogens and the oxygens. Over here, I have 2 oxygens and 2 hydrogens plus 2 hydrogens gives me 4 hydrogens. Over here, currently, I have 1 oxygen and 2 hydrogens, but I can fix that by adding a 2 out front there. That will make it 2 and 4. All right, so make sure to balance your chemical equation. Now, when I write my complete ionic equation, I'm going to break apart my aqueous compounds. So complete ionic. I don't get to break up my magnesium hydroxide because it's a solid. So this stays MgOH2 solid. But now I get to break up my aqueous hydrochloric acid. I need to make sure to carry that 2. So 2H plus AQ plus 2Cl minus AQ. Magnesium chloride is also aqueous, so Mg2 plus AQ plus 2Cl minus AQ. Notice that this 2 comes out front when I make it to my net ionic. And then just like you don't break up things with the solid subscript, you also don't break up things that have this liquid subscript, like water. So this would be H2O, whoops, need to keep it balanced, 2H2O liquid. So then when I'm moving to my net ionic equation, the only thing that I really get to cancel are the chlorides, the 2 chlorides that are on both sides. So this, my net ionic would be MgOH2 solid plus 2 H plus aqueous gives me Mg 2 plus Aq plus 2 H2O liquid. So that would be my net ionic equation.